Hello everyone. In this video, we are going to talk about chapter 13, section 13.4. So, in the past, in the previous video, we learned about we emphasized highlighted Newton's second law equation of motion says F equals ma. This equation is best used when problem requires finding forces, especially force perpendicular to the path, acceleration, velocity, or mass. Remember, unbalanced force causes acceleration. When there's a force, there's always acceleration going with the force, according to Newton's second law, F equals ma. Three scalar equations can be written from the vector equation. The equation of motion, being a vector equation, may be expressed in terms of three components in the Cartesian rectangular coordinate system. So sigma f equals ma, or we can break it into the three different directions, the ijk component, ijk direction. So sigma fxi will be corresponding to maxi, and then sigma fy will be may on the j direction, and then sigma fz will be corresponding to maz on the k direction. Okay, so keep going. Free body diagram, we're always needing it. It's always critical. You're going to establish your coordinate system and draw the particles free body diagram showing only the external forces. These external forces usually include the weight, normal force, friction force, and applied forces showing the ma vector, sometimes called inertial force, on the separate kinetic diagram. Make sure any friction forces act opposite to the direction of motion. If the particle is connected to a elastic linear spring, a spring force equal to Ks, spring constant times the um, distance of the how much spring is being stretched or compressed. This should be included in your free body diagram as well. So in your equations of motion, if the forces can be resolved directly from the free body diagram, usually often the 2D cases, 2D problems, we're going to use the scalar form of the equation of motion. If more complicated problems, such as 3D problems, a Cartesian vector is written for every force, and the vector analysis is often the best approach. A Cartesian vector formulation of the second law says F equals ma, or F sigma fx on the I direction, plus sigma fy on the j direction, and plus sigma fz on the k direction. That will equal to ax on the I direction, ayj on the j direction, and then az on the k direction. Three scalar equations can be written from this vector equation. You may only need two equations if the motion is in 2D. Kinematics. The second law only provides solutions for forces and accelerations. If velocity or position have to be found, kinematics equations are used once the acceleration is found from the equation of motion. Any of the kinematics tools learned in chapter 12 may be needed to solve the problem. Make sure you're using consistent positive coordinate directions. So other words, if you want to define positive going to the right, it always going to the right positive. If you want to define going up positive for your y component, always going up being positive. Let's take a look at two examples together. First one says I have a motor that wings the cable with a constant acceleration such that there's this box 20 kilograms, and in 3 seconds it moves a distance of 6 meters, and we know the friction coefficient mu k, kinetic friction coefficient, equals 0.3. We're looking for the tension developing the cable. We're going to draw our free body diagram and the kinetic diagram. In the free body diagram, it shows all the forces. Weight is always there going straight down. Normal force will always be perpendicular to the surface. We have the tension pulling up. We have the kinetic force, kinetic friction that is going to be parallel to the contact surface. And then the one on the right hand side of the equation will be our ma, mass times acceleration. Your mass is 20, acceleration we don't know, so keep that a there. So we're going to write our equation. Since we know that this block moved 6 meters within that 3 seconds. 3 seconds move 6 meters. So we're going to plug into this equation. This will help us calculate relating the acceleration, velocity, and distance. We know the distance, we know the time. We can calculate the acceleration. How much acceleration do we have? from this for this block. Knowing the acceleration, remember our free body diagram here. Let me try to draw it here. We have our force coming down, okay, and we have normal force perpendicular to the surface, and we have our friction force that is always going to be opposite of direction of movement, and we also have the tension going up. So these forces, we're going to put them in two different direction equations. So we are going to define perpendicular to the surface this way as our y-axis. Ooh, that's an ugly y. We are going to do perpendicular to the surface as our y, and then we're going to along the surface being the x. Okay, we know our x, we know our y direction. Now we can write our equation. This one is my weight. Weight is going straight down. Now notice that x and y, none of them is going straight down. So we're going to break our weight into along the w, break it into two components. One of them will be along the the inclined plane. The other one will be perpendicular to the inclined plane. So this one right here depends on our angle, right? Where our angle, since our 30-degree is in our the angle of our inclined plane, that means your 30-degree is also here. So this component right here will be cosine w cosine 30, and then the other component along the inclined plane will be w sine 30. I'm kind of running out of room there. Okay, so vertical direction, well, not vertical, y direction, because y is perpendicular to the inclined plane. On the y direction, you have normal force that is going up. This one is your normal force. This one right here is my normal force perpendicular to surface and going up. Okay, positive normal force, and you have negative 20g. 20 is the mass, right? We have 20 times g and then cosine 30, which is referring to this one. On the x direction, you have tension going up. We define to the right, going up along the inclined plane toward the direction of the motor is positive. So you have positive t, and then you have minus 20g sine 30, minus 20g sine 30, which is the other component of our weight. And also we have a friction. Friction is going the opposite direction of the motion, which will be kinetic coefficient, kinetic friction coefficient times the normal force, which is m. So putting these two equations together, oh, right hand side, sorry. On the vertical direction, your right hand side will be a zero because um, there's no movement along the y direction. All of our movements is along the x direction, which is along the inclined plane. So for your x equation, your right hand side is going to be ma will be 20 times a. So putting these two equations together, I have two equations and two unknowns. From the first y equation, I solve for the value of the normal force, and from the second equation, I solve for the tension T. Okay. And then that's all I want to show you on this example. Next one, we have another group problem. This one says I have a 300 kilogram bar B moving originally at rest, and with this motor, a series of small roller at the bottom with a motor end pulling up, through this cable, through the pulley, and it's moving at a rate of velocity equals 0.4 time square. Okay, where time is in second. We're looking for the force in the cable and distance s when t equals 5 seconds. And again, we're going to first draw our free body diagram. This thing is not an angle. That free body diagram for the block is we always have a weight coming down, normal force perpendicular to the support surface, and then the tension pulling to the right. And then on the right hand side, the kinetic diagram will be ma. We're going to write out our equation. So horizontally, really that's all you need, because vertically we have the weight and the normal force, and we can conclude that your weight equals the normal force. That's along the vertical direction. So what we're interested in, or our story, is really about the horizontal direction. Along our horizontal direction, you have fx, which is 300 times a, right? That's F equals ma, that's your ma, which meaning the only horizontal force is your tension. That means your tension equals 300a. Now, since velocity equals 0.4 t squared, that's given in our problem, taking the first derivative of velocity with respect to time, that gives me 0.8 t. That is our equation for acceleration. Acceleration equals 0.8 t. And then our tension equals 240 t. Tension equals 240 t. Okay, where does it come from? If you get a little confused, what we're doing is tension equals 300 times A, right? And because A equals 0 0.8 T, you plug in this for the value of A. That gives me 240 T. Okay, and we know that time is at 5 seconds. Time is at 5 second. Plug in right here. We can get the tension at, that will be at 5 seconds. That will be 1200 Newton. Keep going. Since we know t equals zero point 0.4 t squared, velocity equals zero point 0.4 t squared, we can take the integral to get our expression for position with respect to time. And again, we plug in the value of t equals 5 seconds. We can get our distances traveled 16.7 meters. Okay, that's all I want to show you in this section. Hope you find this video helpful. Thank you for watching.